series of basic concepts of classical mechanics lecture. Today our topic of interest is conservation theorem for a particle. There are three conservation theorems which are obeyed by the particle. One is conservation theorem of linear momentum, another is conservation theorem for angular momentum, and the last one is conservation theorem of energy. We will discuss it step by step. First, we will take conservation theorem for linear momentum. You very well know that what is linear momentum. If a particle is moving in a straight path, let us consider the particle is moving in a straight path having mass m with velocity v. We know that the motion of the particle is given by its linear momentum, and the linear momentum is given by mass and velocity. If we are taking single particle system, then the momentum of the particle is also single having mass m and velocity v, that is the product of mass and velocity. The direction of the momentum is in the direction of the velocity. If this is the direction of the velocity, then this is also the direction of momentum. Now, for every conservation theorem, there is a condition. If we have to consider linear momentum is constant, it means somewhere there is some condition which makes linear momentum constant. Here from Newton's second law, that gives a relation in between the external force on the particle and rate of change of momentum of the particle with respect to time period. Here we find out at what condition linear momentum is constant. Let us consider this quantity should be constant, or this quantity will be constant only when the change in the momentum is zero. If the change in the momentum is zero, then 0 upon something, that will come out to be 0. It means the condition should be if the external force applied on the particle is 0, only then the linear momentum that should be equal to 0. When external force applied on the particle is 0. This is the force which we applied on the system or on the particle by external sources. These are not the internal sources. These are not the forces due to the mutual interaction in between the particles, mutual interaction or repulsion. When external force is 0, from this condition or from this relation, if f is equal to 0, dp upon dt comes out to be 0. Here dt is not equal to infinity. We are taking a finite interval of time. If dt is not infinity, then dp upon dt will be equal to 0 only when dp is equal to 0. If dp is equal to 0, it means the change in the momentum. D stands for the change. Change in the momentum is equal to 0. If the quantity is not changing, it means the momentum is constant, or you can say that it is conserved or it is not varying. This is the conservation theorem of linear momentum. Then how will you state conservation theorem of linear momentum? We state conservation theorem of linear momentum such that when the external force applied on the particle is 0, then the momentum of the body or the particle remains unchanged. It means the momentum is a constant quantity. Here the momentum is a constant quantity only when the external force on the particle is 0. Then what is the condition for which momentum remains constant? The momentum will remain constant when the external force applied on the particle is 0. Second is law of conservation of angular momentum. Here we very well know that if we are considering the particle is in circular motion or angular motion, then the study of motion is known as angular momentum. Here in our case, let us consider O is the center of our circle in which the particle is moving, and the radius of the circle is r, and at any time t is equal to 0, let us consider the particle is at a and having velocity v. After some time t, the particle, let us consider the particle is moving in anti-clockwise direction, and the particle is at any point b, and now the direction of the velocity is along the tangent at the point b, that is the point of contact. uh, Here the magnitude of the velocity at point A and point B is the same, but as the direction of the velocities are not same, then we can say that V is not equal to V dash, but here V magnitude is equal to V dash magnitude. Both velocities are same in magnitude, but they are not same in direction. Hence, every point there is a change in motion. If the particle is having a mass m, then at point A, the linear momentum is p and it is given by m into v. And at point B, the linear momentum will become p dash and it is given by mv dash. This is the case when the particle is moving in circular motion, in rotational motion, or in angular motion. Here r is the radial vector, and if the particle is lying at point A, this is the direction of r. This is the radial vector r. Angular momentum theoretically is given by the cross product of radial vector and the linear momentum. We can't interchange the position of r and p. We can't interchange these two vectors. We can't write here p cross r because cross product is an anti-commutative. This is r cross p, and it will be equal to minus p cross r. It means the cross product is not commutative. If it is commutative, then the cross product r cross p should be equal to p cross r, but in cross product uh, this product is not commutative. Theoretically the angular motion is given like this, and practically if we discuss what is angular momentum, it is the motion of the particle, study of motion of the particle when the particle is moving in a circle or in a rotational path or in an angular path. But how you will find out the direction of angular momentum? Just twist your right hand fingers in the direction from R to P, then the thumb of your right hand will give the direction of L. From here, let us consider if this is the direction of R and this is the direction of our angular linear momentum, in our case at position A. This is the direction r of radial vector, we have taken this, and this is the direction of velocity, and this is again the direction of momentum. Also, this is the direction of your linear momentum. If we curl our fingers of right hand from R to P, that is from R to P, then thumb indicates in the upward direction. It means the angular momentum is in upward direction. From right hand curl thumb rule, we can find out the direction of L. Now everything about L is now known. L is a vector quantity. Its direction is perpendicular to R as well as perpendicular to P. Theoretically, it is given by the cross product, and we can calculate with the help of the cross product. And if you want to explain it, it is the study of motion when the particle is in angular motion or in rotational motion. Now, the particle moves in a curve or in a angular motion or in a rotational motion only when there is a torque applied on the particle. Now let us consider your case of a cycle, when you use a cycle, then what happens, you put your both hands on the handle, and when you move this part of your handle towards your side, then the other part automatically moves with in the far away side in the opposite direction. Let us consider you applied a force F here, then you will experience a force F here also, and this is the smallest distance in between these two forces. These two forces are not applied at the same point. This is not like the case here. If this is any point or in any body, then if you applied a force in upward direction and you are applying a force in downward direction, then the net force on this particle should be equal to 0. But here we are not applying the force on a common particle, we are applying the equal and opposite forces by a separation of distance in between them, that is a radial separation or radial distance. Hence the torque, and due to these two equal and opposite forces, this handle will start to rotate. This couple of forces produce a rotation in your handle, and this bending moment or moment of a force, that is known as torque. And bending moment of force mathematically can be represented with the help of torque and given by the cross product of radial vector or the perpendicular distance in between the two forces which are equal and opposite to each other. This is our torque, that is the moment of force. Moment of force, that is known as torque. That is the theoretical definition of torque, and this is the mathematical definition of torque. And what is the direction of torque? Torque is in the direction which is perpendicular to the radial vector and which is perpendicular to the force also. If we consider R is along x-axis, F is along y-axis, then what is the direction of torque? Torque will be along z-axis. The cross product of two vectors give a vector, but this vector is in the perpendicular direction of both of these two vectors. This is torque. The relation between torque and angular momentum, because here we are going to study the law of conservation of angular momentum. There is a relation in between linear momentum and between torque and angular momentum. As we know from the definition of angular momentum, L is given by cross product of radial vector and your linear momentum, and from definition we know that the torque is given by R cross F. These two are the mathematical definitions of angular momentum and torque, and from this relation we can consider torque, or we can change torque in the form of linear momentum, because from second law of Newton's motion, F is equal to dp upon dt, we can substitute this term in the above relation and we can change torque into linear momentum. Hence tau is equal to r cross f, and instead of f we can put dp upon dt, and instead of p we can also put the value of p, that is m into v. We can put here, and in our equation of torque we can put r cross t upon dt and m into v, and let us consider this is our equation number 1. Now we have to find out for angular momentum, and the angular momentum is given by L is equal to R cross P, and this R cross P, if we differentiate it with respect to time period, what will you get? First of all, we will take this as a constant and differentiate p with respect to time. And in the second term, we differentiate r with respect to time and we will take this as a constant. Then r cross dp upon dt plus dr upon dt cross p, and instead of p we can put the value of p, that is mass into velocity. We will have r cross d mv upon dt plus dr upon dt. Instead of dr upon dt we can put v, that is velocity displacement upon time taken, and cross m v. Here v is in cross product with v, not with m. M is a scalar quantity. Only the two vectors can be in dot product or in cross product. M is a scalar quantity here. Then we have to find v cross v, and we very well know that it is equal to 0, because v cross v means magnitude of v, magnitude of v, and angle in between them. Both are same quantities, then what will be the angle in between them? That is equal to 0. Hence we get v cross v is equal to 0, and this term becomes 0, and we will have d r cross p upon dt, that is can be written as r cross d m into v upon dt, that is r cross d mv upon dt. This is our expression, and this is our term on which we differentiate, that is r cross p. What is r cross p? It is nothing another than your angular momentum dl upon dt. This is r cross p, and this r cross p can be written as L. On the right hand side you will have r cross t mv upon dt, and this is nothing else more than our first term, that is r cross t upon dt mv, that is our torque. It means this is the relation in between torque and angular momentum. And now find out the condition. At what condition the angular momentum from this equation can be constant? If you put external torque applied on the body is 0, then the change in angular momentum with respect to time period becomes also 0. It means time is not infinity here, time interval is not infinity. This quantity may be 0 only when the dl is equal to 0. If we are making dl is equal to 0, it means there is no change. D is representing the change in the angular momentum. It means there is no change. If there is no change in the quantity, and it means the quantity remains conserved, or it means the quantity is constant. Hence, in law of conservation of angular momentum, we find out that there is a condition when applied on a body in angular motion, only at that condition angular momentum is constant, and that condition is torque, external torque on the body is equal to 0. What will you conclude from these two law of conservation of linear momentum and law of conservation of angular momentum? You find out that at one condition one quantity is constant. In case of linear momentum, when external force is 0, then only then the linear momentum is constant. And in case of angular momentum, when external torque is 0, only at that condition the angular momentum is constant. Hence, in the law of conservation of any physical quantity, there are two things. One is the condition and another is the physical quantity which remains constant. Now, we move towards our third law, that is law of conservation of energy of a single particle. Till we are discussing the law of conservations on a single particle. Third is law of conservation for energy. Then what is law of conservation of energy? Here the term is indicating that energy is constant. but there should be a condition where the energy remains constant. In our case, if a particle is moving, it is changing its kinetic energy as well as potential energy, then the total energy of the particle is constant only when the applied force on the particle is conservative one. If the applied force on the particle is conservative, only at that condition the energy of the system or of the particle remains constant. Here, in our further discussions or mathematical calculations, we will put kinetic energy with T and potential energy with V. We will show, symbolize, and these two energies like this, and E is the total energy. Now we will prove that T plus V is equal to E, and it is a constant quantity. Energy can be proved constant if initial kinetic energy plus potential energy becomes equal to final kinetic energy and final potential energy. Let us consider the particle have a force F, and that is a conservative one. You have applied a conservative force on this particle, and the particle, when at position A, having kinetic energy T1 and potential energy V1, and at any point B after time T, the kinetic energy becomes T2, and let us consider the potential energy becomes V2. And in our first case, the at position A, let us consider the velocity of the particle is v1, and at B the velocity of the particle is v2, and the particle which is moving with conservative force, let us mass is m. These are the things which we are taking to explain our system, what system we are considering. Now, how we will define work, because work is related with energy, energy is work, and work is energy. Here, in our first case, we are converting or finding out the expression in between work and kinetic energy. We can, with the help of definition, define work as F dot ds, but the particle is moving from A to B. Then to find total work, we have to integrate this whole equation from of the right hand side, as the particle is moving from A to B. Now we want all this expression in the form of kinetic energy. Then we have to find out the relation in the terms of mass and velocity. We can convert force into momentum with the help of second Newton's law. F can be represented as dp upon dt, and if we multiply and divide by dt, we will find this term is nothing, it is velocity. And here we can substitute the mathematical value of p, that is mass into velocity. Mass is not changing with respect to time. Then if we put p is equal to m into v, we are not changing mass with respect to time. Mass behaves like a constant quantity. We are changing velocity with respect to time. Then we will get dv upon dt. And this quantity ds upon dt, it is velocity, and this is another and term dt, and we will cancel out this, and we will get m v dv. And if we integrate, we will have half of m v square, because we will get v dot v, and v dot v, that is v square. And at position A the velocity is v1, and at position 2 the velocity is v2. Substituting these upper limits and lower limits, we will have half of m v2 square minus half of m v1 square. It is nothing, it is the final kinetic energy and initial kinetic energy. Hence the work done from moving the object from A to B with the help of a conservative force. It is given by T2 minus T1. Let us consider this is our equation number 2. Similarly, we will find out the relation in between work and potential energy. In our last expression, we know that the work and potential and force and potential energy have some relation. The force, if the force is conservative one, only then the force is given by minus gradient of potential energy, and in symbolic form the gradient can be represented with the help of del operator. And to find out work done, we have to find F dot ds. Then what will be F dot ds? In the terms of potential, we will get minus del V dot with ds. And in the left hand side, we know that this is the small work done. And if we want to integrate it, we will get the total work done, and on integrating we get this value minus del v dot with ds from position A to position B. dv that is the gradient of potential. Gradient of potential can be written in the form of change of potential with respect to change of displacement. Hence we can substitute the value of del v here, and ds will be cancelled out, and we will have minus dv from position A to B. And at position A the potential energy is V1, and at position B the potential energy is V2, and on integrating dV we will get minus V, and position A we have potential energy V1, and at position B we have potential energy V2. Substitute this upper and lower limit, we will get minus V2 plus V1. Arrange this term and we get V1 minus V2. That is change in the potential energy. This is nothing. This is the work done on the body or work done by the body. And this, let us consider this is our equation number 3. If we find that equation number 2 is also giving the work done from A to B, and equation number 3 is also representing the work done from A to B, it means these both work dones are the same quantities. Hence we get T2 minus T1 is equal to V1 minus V2. The terms with 1 1 representing the initial kinetic energy and the initial potential energy, and terms with subscription 2 2 representing the final potential energy and final kinetic energy. Hence, if we rearrange these terms, we will get that is T2 plus V2 is equal to T1 plus V1, that is the total kinetic initial energy is equal to total final energy. The combination of kinetic energy plus potential energy represents the total energy, and in our case the initial energies are equal to the final energies, hence the total energy of the system remains constant. This is the law of conservation of energy, and it will remain constant. Energy will remain constant only when the force applied on the system is conservative one. In our next lecture, we will deal with the system having large number of particles and the concept of center of mass.